let's do some guided practice on optimization. Some of these problems will be easier than others. Some of them won't even require us to come up with the equation, or the function rather, to maximize or minimize, which is kind of nice. But then the trade-off is that the differentiation might be a little more challenging. Anyway, let's take a look at this first one. Two numbers whose difference is 100 and whose product is a minimum, right? So we know, I guess we want to minimize the product of two numbers. I guess we'll call it P equals xy. With constraint, right? They don't call it the constraint, but it's implied that the constraint is x minus y equals 100, right? Now you could say, well, how do you know it's not y minus x equals 100? Well, it doesn't matter, right? Choose one, right? All right. Well, hold on a second. If x minus y equals 100, then I guess you could say that x equals 100 plus y. So really, P equals xy, which equals 100 plus y times y, which equals 100y plus y squared. All right. So now we can minimize. Now we can minimize. Let P prime of y equal 100 minus, plus 2y equals 0. So y equals negative 50, and I guess that means that x equals, well, if x equals 100 plus y, then x equals 50. Right, because their difference is 100. Their product is a minimum. Yeah, that looks pretty effective, right? Let's just make sure that we do, in fact, have a minimum, right? Plug in a number less than negative 50 into P prime. You get negative. Plug in a higher number, you get positive. This is a chart for P prime, so we're good. Let's take a look at number 2, right? Field biologist wants to enclose a rectangular study plot, 1,600 feet of fencing. Now, this isn't quite as bad. This is similar to that first example that we did. Maybe not quite as bad. We don't have to worry about that false non-material side, right, with the river or whatever. Anyway, it's the same sort of thing, right? You just do that. All right, okay. I guess we've got x here, y here. If you want to keep writing it, then whatever. So I guess we want to maximize our area, which is a equals x times y. Our constraint is that the perimeter has to be 1,600 feet. So that's 2x plus 2y equals 1,600. All right. And so that means that, I guess that means that y equals, if we divide by 2, we get 800 minus x, right? Divide both sides by 2, x plus y equals 800, subtract x. And that means that a equals xy, which equals x times 800 minus x, and that equals 800 x minus x squared. So we're going to let our area, well, I should say the derivative of our area function, equal 0. So x equals 400. Okay? Now what did they ask for? Determine the dimensions, right? Oh, sorry. We also want to make sure that we do, in fact, have a maximum, right? But I think it's, pretty clear that we do. All right, so we're good there. The dimensions, if y equals 800 minus x, I guess then we have... Right, and so you notice, I guess the maximized area for a rectangle results from the area of a square. And that should make sense because this is a pretty symmetric situation here, right? There were no constraints on the length of x and y or the number of sides or blah, blah, blah. So you would expect them to have the same length. I guess we should be a little careful with units, right? Maybe I should write... There you go. Move on, maybe move this over a tiny bit there. There you go. There you go. All right, there we go. So now here we get to the ones where I was like, look, they give us the function that they want us to maximize, right? Maximizes yield, right? We're trying to maximize y. We don't even need a constraint here because we already have the equation, right? So maximize y of n. So we're just going to let y prime of n equal 0. Well, low d high minus high d low, let me just, all over low squared equals 0. Well, then that means that I guess we get that 1 minus n squared all over n squared plus 1 squared equals 0. And that, of course, implies that, I think maybe you can see this, n equals -1 and 1. Of course, being -1 is nonsense, right, because we've got that. And I don't think they give us... Yeah, they don't give us any units, so we're fine there. They say find the nitrogen level that maximizes yield. Okay, well, there's our nitrogen level. Let's just ensure it's a max, but it should be, right? You plug in 0, you definitely, I guess plugging in 0 into y prime clearly gives you a positive, and then plugging in anything bigger than 1 clearly gives you a negative, so we're good on that. All right, aluminum soda cans are shaped a lot like a right cylinder, and hold 12 ounces of liquid. We definitely want to minimize the amount of material being used, right? Requires a lot of energy, right? Costs money, so let's try to minimize the cost by minimizing the amount of material. This is definitely one where we want to draw a picture, right? Right soda, or right cylinder, right? Something like that. All right, we get that. And I guess we know that it's got a radius r and a height h. And the volume equals 12 ounces, right? 12 fluid ounces, that is, right? Right, whatever. All right, so what have we got here? We're trying to minimize surface area, which I'll just call A. Maybe I think I called it SA before, so I'll call it SA. You just call it A. Book usually calls it A, whatever. Now, do you remember the surface area of a cylinder? It's 2 pi r, right? The circumference of this top circle times h. So what's the constraint? The constraint is actually the volume. It's, now remember what the volume of a cylinder is? It's pi r squared, pi r squared h equals 12. Which implies that h equals 12 over pi r squared. All right, so then we substitute this back in. We get surface area is going to equal 2 pi rh, which is 2 pi r times 12 over pi r squared. And I guess the pi's are going to cancel. Actually, one of the r's are going to cancel. And we wind up having 24 over r. All right. So we're just going to let the surface area, I guess prime of r, equals 0. Well, what's the surface area going to be? Oh, shoot. I'm sorry. I messed this up a little bit. Surface area is 2 pi rh. I forgot to include the tops right here. Sorry about that. That makes much more sense because that wasn't going to equal 0. Anyway, this is going to be plus 2 pi r squared, right? I forgot about the tops and the bottoms. Let me just highlight that real quick. Sorry about that, guys. Okay, so surface area equals that plus 2 pi r squared plus 2 pi r squared plus 2 pi r squared. There we go. All right, so now we're going to get good because this is going to be negative 24 over r squared plus 4 pi. Let that equal 0. Now, I guess again, r can't equal 0, so we don't need to worry about dividing by 0. So instead, we're just going to multiply both sides by r squared. Negative 24 plus 4 pi r squared equals 0. And then this is going to imply that, I guess if we divide by 4, maybe divide by 4 pi, we're going to get r squared equals, r squared minus 6 over pi equals 0. And this implies that, right, we could factor this into, I guess it's r minus the square root of 6 over pi, r plus the square root of 6 over pi equals 0. And that implies that r equals negative root 6 over pi, which is nonsense, or r equals positive root 6 over pi. All right, now let's see. They say what dimensions. Okay, so I guess we need to come up with the height as well. First, we're just going to make sure that we, in fact, have a minimum. If we just can't plug in 0, plug in, let's see, 6 over pi, that's like the square root of 2. Plug in 1. That's less than the square root of 6 over 2. You get a negative. Plug in 2. You get a positive. All right, this is for SA prime. We're good to go. All right. And we also have that h, right, we're going to need to have h. H is going to equal 12 over pi r squared, which is pi times 6 over pi. So let's see, these cancel. And it looks like we're left with 2. So that's our answer. R equals root 6 over pi. H equals 2. I think we've got one more, right? Yeah. Stone is thrown straight up from the roof of an 80-foot building. The height is given by that equation. So another one, right, where they actually give us the function. So we don't need a constraint or anything. So the maximum height, right? Okay, just be a little careful about answering the question, right? We're going to let h prime of t equals 0, right? And that's going to be 32t plus 64 equals 0. I think it's pretty clear then that t equals 2. 2? Oh, wait, sorry, that was negative 32. That makes more sense, right? T equals 2. Okay. So t equals 2. And to be clear, that's 2 seconds. Now, first we're going to make sure that we have a maximum, which we do. 2, if you plug in 0, you're going to get a positive. Plug in 3, you get a negative into h prime, so we're good to go. What's the maximum height? So the stone's max height is, now be a little careful here, what's it going to be? H of 2. And that equals, I don't want to do that out. It's not that bad, though. Negative 64 plus 128, or 2 times 64, plus 80. I think it's going to be 144. I think that's given in terms of feet. There you go.